Welcome to today's Explainer. Today, we're unraveling a physical puzzle you've probably seen a million times. Why do some things plummet straight to the bottom of the water, while others just bob effortlessly right on the surface? You know, dropping a tiny coin into a fountain and watching it sink, versus seeing a massive cruise ship pull into port. The physics behind this is absolutely fascinating, so let's just jump right in and break it down.
To kick things off, we really have to ask ourselves one core question. What actually determines if an object sinks or bobs? It's definitely not just about weight. I mean, if it were, a tiny little pebble wouldn't sink while a gigantic wooden log floats, right? There is a hidden relationship at play here, a very specific balance of properties that completely decides the fate of everything that hits the water. Okay, let's dive into our main culprit, density. Scientists represent this with the Greek letter rho. But simply put, density is just an object's mass divided by its volume. Think of mass as the amount of, well, stuff making up the object, and volume is just the 3D space it takes up. It's kind of like packing a suitcase. The more clothes you cram into the exact same bag, the denser it becomes. And it's this property, not just weight alone, that really holds the key to our mystery.
And you can see this packing idea brilliantly at the atomic level. Just look at how tightly jammed the atoms are in a solid compared to liquids and gases. In a solid, those atoms are locked super close together by strong forces, giving it a really high mass per unit volume. In a liquid, the molecules still take up space, but they flow a lot looser. And in gas, those molecules are spread wide open, just moving freely. So that's what mass per unit volume actually looks like if we could zoom all the way in.
Section 1. The core comparison. Wood versus brass.
Let's run a quick mental experiment, okay? Imagine we take a block of wood and a block of brass. Now, let's say they weigh exactly the same on a scale. If we drop them into a tank of water, they behave totally differently. The wood floats, but the brass sinks straight down. Why is that? Well, it's because the wood has a lower density than the water. Its atoms are spread out. The brass, on the other hand, has all that identical mass crammed into a tiny space, making its density way greater than the water's. When it comes to floating, density is the ultimate judge.
Section 2. The invisible push, Archimedes and buoyant force. But to really grasp what's happening here, we have to talk about the upward push from the fluid itself. This brings us to Archimedes' principle. It famously states that the buoyant force pushing up on an object is exactly equal to the weight of the fluid it displaces. Basically, when an object enters the water, it shoves fluid out of the way, and that displaced water actually pushes back. If the upward buoyant force is greater than the object's downward weight, it floats. Less, it sinks. It is literally a tug of war between gravity pulling down and buoyancy pushing up. Now, what is truly fascinating is how an object's shape completely alters this tug of war. For example, drop a solid lump of clay into water and it drops like a stone. Why? Because it barely pushes any water out of the way. But, and this is a real game changer, if you take that exact same mass of clay and mold it into a wide, hollow boat, everything changes. The boat shape forces a massive volume of water out of the way, which creates a much stronger upward buoyant force. It's the exact same mass, but a completely different result, all thanks to its shape.
Section 3. The grand application. How heavy ships float.
So let's look at Archimedes' principle in action on a massive scale. An unloaded cargo ship naturally floats pretty high in the water. But load that exact same ship up with incredibly heavy cargo containers and its total weight obviously skyrockets. To stay afloat, it has to displace a larger weight of water to generate a stronger upward buoyant force. Because of this, it naturally sinks much deeper into the ocean until the displaced water equals its new, heavier weight. And scientists can actually calculate exactly how deep that ship will sit. It all comes down to a fraction, the object's density divided by the fluid's density. Basically, a ship will successfully float as long as its overall average density stays lower than the surrounding water. And honestly, this is the big secret behind massive steel ships. The steel itself is way, way denser than water. But a ship isn't a solid block of metal, right? It's a hollow shell filled mostly with air. So when you average out the dense steel and that massive volume of light air inside the whole ship's average density ends up being lower than the ocean. To wrap up our explainer today, I want to leave you with one final provocative thought. We've just seen how average density is the absolute key to keeping thousands of tons of steel safely afloat. But knowing that math, what physical fate awaits a ship if it takes on so much cargo, or let's say springs a leak, that its overall average density finally surpasses the water beneath it? I think we both know the answer to that sinking feeling. Thanks for exploring this amazing scientific puzzle with me. You'll definitely never look at a floating ship the same way again.